Okay, welcome to the third example in review of statics. The question reads, determine the minimum cable force T and the critical angle theta, which will cause the tow truck to start tripping. Assume that the truck is parked and will not slip at point B. The truck has a total mass of 4,000 kilograms and a mass center at point G. So with any question, we are going to start off with givens. And in terms of what you're given in this question, like in terms of specifically values, you're not given much other than the dimensions on the diagram and that the mass of the truck is 4,000 kilograms. Okay, what else do we put in givens? Well, we put equations, but the only equations that come to mind for me at least are like the sum of the moments equal to 0 or the sum of forces equal to 0. These are fundamental things, so you don't need to clutter your work with this unless, I mean, you can write them if you want, but it's just clutter in my opinion. When we get to more newer equations, then those you can write down, like the moment equation and stress and like the normal stress and shear stress and whatnot. Okay, we're done with equations, we're done with values. Let's go on to notes that we can put in givens. Well, in terms of notes, we are given that the mass center is at point G. So Fg, or the weight of the truck, acts at point G, and we're also given that there's no slip at point B, which basically means that this force right here is static friction. So it's a static friction force, and if you imagine this point B to be an axis going in and out of the page, the truck will rotate about this point. Okay, perfect. Those are the two notes that we have in this problem. So we said that no slip at B, and we also said that Fg acts at point G. Perfect. We're going to move on to unknowns, and the unknowns in this question are, we want to find the critical angle and the minimum tension force that this truck will tip at point B. So we're going to write that down as well. Minimum tension force and critical angle. Perfect. And one point about these two is that, and which we will do a lot of thinking later on in this question regarding this concept, that this truck will only tip at a very specific, the instant it begins to tip, you will have a very specific minimum tension value and a very specific critical angle value. Any other values won't work to begin the tipping process at the instant it begins to start tipping. But we'll get into that a bit later on. Okay, so the free body diagram, I'll just draw a quick one just to prove that it does not take that much time, even though I might take a bit of time, because I'm a professional artist, you know? Very cool stuff. There we go. Wonderful stuff. That is 1.25. This lovely guy is, this is A, this is B, this is G. You have tension force there, theta. And then lastly, this is 1.5, this is 2.5, and this is 2. Perfect. That's enough for a free body diagram. Okay, so now we include our forces. Well, straight out of the question, we have our friction force acting like so. We'll just call that FB for now. We have our tension force acting on this this rope or whatever, and we can split this tension force up into Tx and Ty, and we can further say that this is just T. Is it sine or cosine? I think it's sine or cosine. I think it's cosine. Cosine theta and T sine theta. Wonderful stuff. What other forces do we have? Well, we also have, that we determined, we have Fg acting at point G, basically the weight of the vehicle. We also have one more force. Some of you may be tempted to say that there's two more forces, but no, there's one more force. And that's the normal force. You may say that we need NA and we need NB. Well, you're right, but only half right, because we do not have NA. Why do we not have NA? Because at the instant, this free body diagram is a capture of the instant it begins to start tipping. And at the instant that you apply this T-force at this specific angle, you will not have a normal force. It will be infinitesimally, I don't know. It'll be like very, very off the ground. Like it'll be just off the ground. That's the way I'm gonna say it, you know? So yeah, so you're not gonna have a normal force A because it's just infinitesimally gonna be off the ground. And you're only gonna have NB. So that's what we're gonna include. Perfect. So you have your 4 forces, and if you have your coordinate system like this, please do not switch around your coordinate system. It's perfect. So now your first thought after a free body diagram is either sum of moments or sum of forces. Normally you would go through sum of forces, but I'm just going to tell you that you're not really going to get anything out of it, because if you just look at it, you have FG in the y direction, you have NB in the y direction, and you have TY and you have TY in the y direction. You don't know T, you don't know theta, you don't know NB, you only know FG. So you have one known and 3 unknowns in one equation. And similarly in the x direction, you have 3 unknowns in one equation. So that's not going to work. So we're going to take the moment. So some moments about a specific point. What point is that? What point are we going to sum the moments about? Well, you want to choose the easiest method, the easiest place where you can sum the moments about. Remember that the moment equation is equal to a distance from the axis cross doesn't really matter here, but like across the force, I guess. So that's the force, that's the formula for a moment. If, for example, we take the moment about point G, this FG force will not be taken into account because the R is 0, and basically that scraps the moment. But we will have to include this guy, this guy, this guy, and this guy. And that looks like 4 forces to me. Okay, what happens if I take the moment at point B? Well, my process becomes a tad bit easier because I only have to deal with FG, which I know, whereas like another con of using NB and FB is you don't know them, so it will literally not bring anything useful. But if I take it about FG, I have, this is my R, right? And I have 2.5 and FG. I will also take TX, and this is my R. And then I will also take TY, and this is my R. This looks like a bit of a mess, but long story short, I only have 3 forces to deal with, and I know one of them. So beautiful, beautiful stuff. So that's what we're going to do. We're going to take the moment about point B. Starting off with FG, as I'll explain it the long way, but in the future, I'll just straight go to the equation. Our distance R and our force, right? So we know FG, this is just equal to 4,000 times 9.81, right? And then R is 2.5, and it will cause, one mistake here is we have to specify what is positive. We're just going to say counterclockwise is positive, and that's how you specify it. Therefore, we're going to have a positive moment because it's going to spin it counterclockwise in our direction that we define as positive. So that's where we're going to start off with. So 4,000 kilograms times, I should have dropped the units, but I started, so might as well continue. Meters per second squared times the distance R, and that is 2.5 meters from where I'm taking the moment. Okay. Let's start back up here. Okay, we're done with the FG force. Now we want to deal with TX and TY. Again, remember, NB and FB are not included in our calculation because the distance, remember, because moment is equal to R times F, we don't have R. They're acting at B. It's 0. Okay, so we don't need to include these. Wonderful stuff. TX, they're both going to be negative. TX is your force, this is your R, which is 3, and then over here, TY, this is your R, which is Ooh, that's actually not good. I should not have done that. Tx, this is 3, and then this is your distance, r, and that is just 1.25. Ty acts right here. Because, again, I could have just went like this, for example. Similar to this way. Okay, but long story short, they're both negative moments because they both want to push the vehicle clockwise, whereas we defined it to be, we defined positive to be counterclockwise. Okay, so wonderful stuff. We're going to say t sine theta times 3 meters minus t cosine theta times 1.25 meters. Perfect stuff. And this is all equal to 0. Okay. You could choose to isolate for theta, but that would be a mess because you have a sine and a cosine, and like the easier way would just be to isolate for tension, and that is what we're going to do. If you do this, you are going to get the tension. You're going to get one of your answers, and then we're going to do some thinking as we as we said. You're going to get tension. The minimum tension force needed to tip this car over is going to be 65,400 divided by cosine theta plus 2 sine theta. Okay, perfect. So we have our minimum tension force, and that's half the question. Great job if you got this far. However, we also need to find our lovely critical angle theta. And to do this, we're going to use this equation. However, we're going to use a concept which needs a diagram to explain. So if we draw this lovely, lovely guy right here. There we go. Okay. We're going to try and explain the relationship between these two. And I'll give you the punchline directly. We're trying to say, at the end of the day, that the derivative after, the instant after it begins to tip, of tension with respect to theta is 0. How the heck did we get to derivatives? Well, I'll try my best to explain it. Basically, let's say the instant we want to make it start tipping. So we have the car, right? And we want to try and tip it about that point, right? Using this tension force, about this point B, as we said before. This will only begin to tip at a very specific tension force and a very specific critical angle. And we'll even give them values, for example. We'll say tension is equal to 5 newtons and theta is equal to 30 degrees. Okay? It will not tip if tension is 40 and theta is 30. It will not tip if tension is 5 and theta is 40, for example. Just to oversimplify things. It will only tip at these two values. It will only begin to start tipping the instant, like less than milliseconds. The instant it begins to start tipping, it will only happen at these two values. Okay, and basically, in other words, that basically says that T is dependent on theta, right? Tension is dependent on theta. Okay, what happens after the instant it begins to start tipping? Well, this relationship is no more. Why? Because you can even think of it like, this is like an okay explanation. Like if you have a box and it's on the ground, it takes more, like this is the concept of static friction versus kinetic friction. It takes more force to get it to start moving than to move it along. And I think the like it drops like static friction. Okay, we're not going to get into that. But anyway, it takes more force to get something start moving, than to get it to just move afterwards. That's the same type of concept. Basically, after the instant after it begins to start tipping, I can technically change the theta value. We're still at 5 kilonewtons or 5 newtons. I can change this theta value to, for example, theta is equal to 30.2 degrees. This is oversimplification, but let's say this works. But this is only after it begins to tip. It won't tip. Like if I started out with these two values, it won't. It will only work with 30 degrees and 5 kilonewtons or 5 newtons, right? But after I begin to tip it, they no longer depend on each other directly. And this doesn't mean that I can change it to 45 and it will still work at the same 5 newtons. No, that's why we have to introduce the concept of derivatives, right? So we're not saying technically that the change in any change in tension over any change in theta is equal to 0. We're saying that the infinitesimal, the very small changes in tension, no longer are dependent on very small changes in critical angle. Hopefully you understand that. If you don't, no problem. All you have to do is plug in the formula, my friends. And how the heck do you do that? Well, basically, you apply a derivative to both sides, right? With respect to d theta. So we're going to basically say we're going to apply this lovely formula to sine theta. Okay, and from this, we're going to get dt over d theta is equal to the derivative, and I'll just skip a quick step here, of d theta times 1 over cosine theta plus 2 sine theta. Why did I bring out the 65,400? Well, because it doesn't have any theta terms and it's not dependent on theta. So by derivative rules, I can take it out of the derivative. Okay, and all of this is equal to 0, as we beautifully explained in our lovely diagram up here. And to be honest, like it's a big jump. Like it's not something you like intuitively catch up unless you practice. Same way like you thought before that you saw a bunch of numbers and like how the heck am I gonna think of two numbers that add to like basically factoring, and then now hopefully you can factor with ease. So it all just comes from practicing these problems. So if you continue with this derivative, you use lovely quotient rule, if you remember that, and we will do that right now. So dt over d theta is equal to 65,400. How I remember quotient rule is low d high, so low sine theta, so denominator times high, or d high, so low d high minus high d low, square the bottom, and away you go. So denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, and there we go, theta, and then square the bottom and away you go. So you square the denominator and then you go to the next step, you know? Yeah, fun stuff. Okay, after a bunch of lovely simplification, and remember this is equal to 0 at the end. This is equal to 0. We're only going to focus on this part of the equation from now on, basically, the 0 part. Because this is equal to 0, you can just divide this out, divide both sides by 65,400, and then divide this side, so therefore this guy goes away, and you also can multiply both sides by this term right here. So if you multiply by cos theta plus 2 sine theta squared, these two cancel out, and then there's 0 on the other end, so it's just 0. What you're left with, and then another simplification is 0 times this guy, so that just cancels out. What you're left, and you can also divide by -1, divide both sides by -1, so you're literally just left with this part right here, and that's what we're going to write. So negative sine theta plus 2 cosine theta is equal to 0. Multiply both sides by 1 over cosine. What you're going to get is negative sine over cosine is tangent, so negative tangent theta plus, if you divide this by cosine, you get 1, so you're just left with 2. So negative tangent theta plus 2 is equal to 0. Once you isolate for theta using this formula, you're going to get that theta is equal to 63.5 0.43 degrees, right? Perfect stuff. And then using the formula from before, if you plug in this theta into here, you're going to get that the tension force is equal to 29.2 kilonewtons. And what this basically means, again, is the same way we described before, that in our theoretical scenario, that tension is equal to 5 newtons and theta is equal to 30 degrees. Similarly, only at theta is equal to 63.43 and only at tension is equal to 29.2 kilonewtons will this truck, like, these two values will make the truck tip at point B. Only, like, it will begin the tipping process. That was a bit of a stretch near the end, like especially this part, but hopefully that was helpful. These are your answers.